All right, momentum we covered a week ago, as well as, I believe, impulse. So first off, what is the formula for momentum? All right. Let's make it to the right positive. 3 kilograms times, we'll just say 10 meters per second. What is the momentum of this object? Try that one again. I have a 3 kilogram object going to the right at 10 meters per second. What's the momentum? Without a calculator.
30.
Yep. Kilogram meters per second. Or if you want a shorter version, that's also a Newton second. Or make up your own unit. And define it. All right, so 30 Newton seconds. So given this is all part of the same umbrella, so let's put that there. I have a 2 kilogram mass going to the left at, let's say, 8 meters per second. What is its momentum?
Would the 2 be negative?
Would the 2 be negative?
Yeah, no.
That's 2 kilograms.
It's just 2 kilograms, no.
Negative mass is a tricky thing to accomplish.
Newtons per second.
Not per second.
Why'd you put the S next to newtons?
It's Newton seconds.
Newton seconds.
Per is when you're dividing by it.
Okay.
So you said 16 Newton seconds?
Yes.
One small issue with that?
Would it be negative?
Yeah. Not the 2's negative, the 8.
Eight's negative.
The negative indicates to the left, so I indicated to the left with the arrow here.
Mhm.
And so I wouldn't write the negative and the arrow to the left at the same time.
Okay.
So it's negative 16 kilogram meters per second. What is the total momentum of this system?
Newtons per second.
I refer to that as Ed's disease. Student years ago, always wanted to put per in between any 2 units that he spoke.
14 Newton seconds.
There we go.
Okay.
Where do you get 14? It's Monica's fault.
Is it wrong?
How do you get 14?
I subtracted 30 Newton seconds by 60 Newton seconds.
What is 14?
That's the total momentum of the system.
How did you get that?
Total is a sum. So that plus that.
Oh.
All right, so there's going to be a collision. And I'm trying to recall, it's been a week, did I talk about open systems versus closed systems? So let's talk about open systems versus closed systems. I have this pin. What is its velocity right now?
0.
Okay. So what is its momentum at the moment?
0.
If I drop it, will the momentum stay 0? All right, so I drop it, it starts moving, momentum is no longer 0. But I talked about conservation of momentum, the total should stay the same. So what happened? Why is it that it moved? Momentum did not seem to be conserved. What happened in order to keep momentum conserved?
What do you mean conserved?
Total is the same before and after. So I started out with 0, I let go, and then before it hit the table, momentum definitely wasn't 0, for the marker at least. All right, so let's just make up some numbers here. We'll make it a 10 kilogram mass. That's about right. I picked it up so effortlessly. The initial velocity, 0 meters per second. We'll just go ahead and make down positive. And so it falls and it's going 2 meters per second. At some point it's going 2 meters per second downwards. So final velocity, 2 meters per second. What is the initial momentum? In units would be really nice right now.
0, 10 times 0, 0.
And my final momentum?
20.
Oh,
No. Seconds.
or kilogram meters per second, or
Okay.
again, whatever you did. All right, so what is the change in momentum?
20. Seconds. Is that a negative? No, it's equal. Okay.
Yeah, that's an equal sign there.
Okay.
All right, so we have a change in momentum of the marker. If momentum is conserved, how can we have a change? And again, momentum being conserved says that at any point my total is still the same.
Can you repeat that definition so I can write it down? You said a change in momentum.
What did I say?
Wait.
If momentum is conserved, that means the total is the same at any point. In this case, we have the marker gaining 20 Newton seconds of momentum. So clearly, the amount of momentum initially and the amount of momentum finally is not the same. So how can we claim momentum is conserved when here's an example where it's not conserved? And by the way, momentum conservation is one of the fundamental principles of physics. What's different about this problem than all the other problems that we did with momentum? What are all the other problems that we did? What was happening in all the other problems? No, all the other momentum problems, generally let's limit to the horizontal ones. Say it
We
again?
had a mass and other problems, and this one we don't have a mass.
10 kilograms.
The total.
What's your ratio?
There's no other force acting.
Nope, that's it. That's the only force. We're ignoring air resistance, of course. The weight's the only thing acting on it.
It started off at 0?
It did start at 0, but it gained momentum. So if momentum conservation is a thing, then if it gained 20 units of momentum, the other one should have a change of negative 20. What other thing would have a change of negative 20?
Acceleration.
Should be another object.
Another object.
were saying? All right. When I went through the derivation that I just, for some of you, let it flow over you. When I went through the conservation momentum formula, what was that first equation I started with?
It was the F, force average equals negative force B times A.
Probably AB.
AB, did I write it wrong? AB.
Say it. Jennifer, you were saying?
So force AB,
Equals.
equal negative F BA.
Yeah. The force on A from B is equal to the negative of the force on B from A. It's Newton's third law. That's the shorthand version of Newton's third law. There's two objects involved. They're exerting an equal amount of force on each other, equal magnitude of force on each other. They collide. In this situation right here, well, in all the other situations, I was going for collisions earlier. We were dealing with a lot of collisions. We have these two objects. So the only two objects, they exert a force on each other. Momentum beforehand equals momentum afterwards. Here, I have only one object, but there's clearly another object involved because otherwise there wouldn't be any, it wouldn't fall if I let go. What is the other object involved?
Your hand,
Once I let go?
the force of the gravity,
Coming from?
the ground, or wherever, yeah, the ground.
So, if I take this marker, this 10 kilogram marker, and I drop it, as it falls, the earth comes up. Now we don't notice that because we still have this tiny little force acting on such a huge mass that we don't notice the earth shifting. I've done calculations before in a different class. I got up on a table, I jumped down. And I jumped down, the distance that the earth should shift is basically the size of a nucleus of an atom. So, which is why we don't notice it. So there are two objects involved here. There's the earth exerting the weight on it, causing it to fall. But this is also exerting a force on the earth, Newton's third law, causing it to rise. Just not very much. If I only look at one of the objects, we see that the total momentum will change. This is an open system. In an open system, we're ignoring some outside influence. In a closed system, there is no outside influence. So in this case right over here, if they collide, it is a closed system if I'm looking at the total. So as long as I'm looking at both objects, the only two objects in this problem, then it's a closed system. If I also brought the weight of each object because of the gravitational attraction from the Earth, or towards the Earth, then I've now introduced another object that I either need to take into account, or if I ignore it, it is an open system. So this is why when I do these problems like this, I'm picturing in my head, it's the universe with only these two objects heading towards each other. I want to ignore the Earth. So
You said two objects is a closed system.
if there's no additional influences from outside what we're looking at, it is a closed system. So in this case right here, if I'm looking at these two objects, they're going to collide, and there's nothing else influencing them, then that is a closed system.
And this one was the marker and the earth, so that, isn't that two objects?
That is two objects, but I only looked at one of them.
In the problem, okay.
Yeah, so
That's
therefore,
why.
because I ignored what happened to the Earth here, that is an open system. The Earth is definitely having an effect on it, but I didn't bring it into my calculations.
Okay.
So open versus closed. Other questions about it?